You are about to hear something that identifies the absolute migration of human technology away from the planet of its birth. For thousands of years, humanity looked up at the night sky as a permanent, unreachable ceiling, assuming that the stars were distant, spiritual entities completely isolated from human touch. This digital reconstruction reveals that in less than a single human lifetime, that ceiling was completely dismantled. The history of space exploration is not just a collection of mechanical triumphs. It is the story of how our species learned to build artificial islands in the dark, transforming the brutal vacuum of space into a grand, step-by-step journey of cosmic discovery. Our slow journey into the space age begins in October 1957 with a persistent, rhythmic beeping sound echoing across the global radio waves. The Soviet Union had successfully launched Sputnik 1, which was the world's first artificial satellite. It was a simple, polished, metal sphere about the size of a beach ball, equipped with 4 external antennas. It did not carry cameras or advanced scientific instruments, but its mechanical presence in orbit triggered a monumental geopolitical shockwave. It proved that humanity possessed the rocket propulsion technology required to overcome the gravitational pull of the Earth, officially closing the book on our planetary isolation and igniting an intense, high-stakes competition between global superpowers to conquer the next frontier. The mechanical momentum accelerated rapidly into April 1961, when a 27-year-old pilot named Yuri Gagarin climbed inside the Vostok 1 capsule. He became the first human being to physically leave the atmosphere, completing a single 90-minute orbit around the planet. For the first time in history, human eyes looked back down at the curve of the Earth from the deep blackness of space. This milestone forever altered our perspective of reality, transforming our giant world into a fragile, beautiful blue marble floating inside an unforgiving void. This profound realization set the stage for the most audacious engineering blueprint of the 20th century, which was the Apollo program. To achieve a lunar landing, engineers had to solve a staggering sequence of thermodynamic and kinetic calculations. They had to construct the Saturn V rocket, a colossal 360-foot-tall machine that generated millions of pounds of thrust, burning through hundreds of thousands of gallons of volatile fuel in mere minutes. In July 1969, this monumental expenditure of human energy culminated in the Apollo 11 mission, when Neil Armstrong and Buzz Aldrin guided a fragile lunar module down onto the dusty plains of the Sea of Tranquility, marking the first time human beings had ever set foot on another celestial body. As humanity mastered local space, our robotic ambassadors began a permanent voyage into the deep galaxy, a phase perfectly embodied by the twin Voyager missions launched in 1977. Instead of relying on massive fuel tanks to cross the vast distances of the outer solar system, engineers executed a brilliant, low-fuel trajectory trick known as a gravity assist. By launching Voyager 1 and Voyager 2 along a highly precise orbital alignment that only occurs once every 176 years, they used the gravitational pull of Jupiter and Saturn exactly like a cosmic slingshot. As the spacecraft dived toward Jupiter, the giant planet's massive gravity pulled the probes inward, accelerating them to extreme speeds and hurling them toward the outer planets. Voyager 1 has officially crossed into interstellar space, sailing into the pristine void beyond our sun as a permanent monument to human curiosity. The modern era of space exploration underwent a major structural evolution. shifting from isolated national sprints to permanent international cooperation and advanced cosmic vision. This transition is anchored by the International Space Station, a massive modular laboratory that has been continuously inhabited by rotating global crews since the year 2000, serving as a vital testing ground for long-duration human survival in microgravity. Alongside this cooperative presence, the deployment of the James Webb Space Telescope has revolutionized our understanding of space. Positioned 1.5 million kilometers away at a gravitationally stable parking spot, Webb's massive, gold-coated mirror acts like a cosmic time machine. Because the expansion of the universe stretches the light waves of the very first stars into invisible infrared wavelengths, Webb harvests these ancient, highly redshifted photons from the dark, allowing astrophysicists to look back over 13.5 billion years to capture the birth of the very first galaxies forming just after the Big Bang. Every slow chapter of this celestial timeline introduces a fascinating, deeply humbling realization. Space exploration has never truly been about abandoning our home planet. Deeper implications suggest that by pushing our technology into the extreme environment of the cosmos, we are forcing ourselves to invent the tools and frameworks required to secure our long-term survival. The history of space exploration has brought us advanced satellite communications, global weather tracking, a deep understanding of our shared planetary vulnerability, and the first steps toward becoming a truly multi-planetary species. We invite a calm appreciation for this ongoing journey. Humanity is no longer just a species that looks at the stars. We are actively becoming a species that lives among them. As private and public coalitions construct next-generation lunar outposts and look toward the red deserts of Mars, the night sky stands not as a boundary, but as an open highway, proving that the true destination of human curiosity is the infinite architecture of the cosmos itself. If you enjoy these deep explorations in space, consider subscribing or hitting the like button. It really helps the channel grow and allows me to make content like this. Human beings have watched the movement of wandering stars across the dark night sky for millennia. The early modern era of tracking these distant bodies required patience and precise mathematical calculations. Astronomers utilized basic optical telescopes to map the predictable orbits of our closest cosmic neighbors. This quiet gathering of celestial data laid the essential foundation for launching instruments into space. The cold, mechanical reality of leaving Earth required solving complex equations regarding gravity and velocity. Initial robotic attempts to reach the upper atmosphere encountered numerous technical challenges and frequent failures. Engineers monitored these brief, high-altitude flights from silent control rooms buried deep underground. Every small incremental gain in altitude provided vital information about the thin upper atmosphere. Eventually, a manufactured object achieved the necessary speed to remain in permanent orbit around Earth. This small metallic sphere emitted a steady, rhythmic beep that signaled a new technological era. Listeners across the globe tuned their radio receivers to hear that lonely, repetitive orbital transmission. The successful launch confirmed that artificial objects could survive the harsh environment of space. Shortly afterward, larger vessels carrying complex scientific instruments were sent toward the circular moon. These early, automated explorers photographed the heavily cratered far side of our lunar companion. The sent images revealed a barren landscape, completely untouched by wind or liquid water. Scientists studied these monochromatic photographs to understand the violent history of the solar system. Each impact crater told a silent story of ancient collisions occurring billions of years ago. The data suggested that the Moon and Earth shared a deeply interconnected geological past. Our understanding of this local space expanded as more sophisticated robotic probes were launched. These metallic travelers crossed the silent void to gather data from nearby planetary atmospheres. Instruments recorded variations in radiation and magnetic fields fluctuating across the vast empty space. The gathered information often challenged existing theoretical models developed by terrestrial physicists over centuries. Uncertainty remained regarding the precise composition of the thick clouds shrouding adjacent planetary bodies. We simply watched and recorded the faint incoming telemetry signals as they arrived home. Now we begin a long, slow journey outward through the historical timeline of exploration. To understand the vast distances traveled by our early space probes, it helps to imagine a scale that fits within a human lifetime. If you were to walk continuously, without stopping for a single moment, it would take roughly 30 years to circle our own planet just a few times. Yet, the distance to our moon is so immense that it could easily hold all the other planets of our solar system placed edge to edge in the quiet gap between the two worlds. When the first crews traveled to the lunar surface, they were confined to a metallic capsule no larger than a standard automobile interior. They lived and breathed inside that tiny pressurized bubble while drifting through thousands of miles of absolute nothingness. The early automated machines we sent to the nearest planets were similarly modest in size, often weighing no more than a simple grand piano. These small collections of metal wires and glass lenses were launched into the dark by burning massive quantities of chemical fuel in just a few intense minutes. Once the engines fell silent, these probes coasted for many months through the quiet dark, powered only by the faint light of the distant sun hitting their small solar panels. The slow communication delay meant that a radio signal traveling from Earth would take several minutes to reach the spacecraft, and the response would take just as long to return home. Scientists sitting in quiet laboratories had to wait patiently for these delayed whispers from the dark, knowing that whatever data they received was already old news from a distant corner of space. This slow pace of exploration reminds us that our human sense of time is uniquely brief compared to the slow movements of the cosmos. Every journey into the night relies on this patient waiting, where months of silent drifting are required to achieve a few brief moments of close observation. The structural foundation of every planetary endeavor demands a complete recalibration of our traditional terrestrial expectations regarding distance and velocity. When we examine the historical logs of early interplanetary missions, we discover an environment dictated entirely by the uncompromising laws of orbital mechanics. A spacecraft launched from the surface of Earth does not travel in a straight line toward its target, but instead enters a sweeping elliptical trajectory around the central sun. This orbital pathway requires precise mathematical calculations performed long before the chemical propellants are ignited on the launch pad. Engineers must anticipate the exact future position of a moving planet, aiming the mechanical explorer toward an empty point in space, where the destination will eventually arrive months or years later. This methodology transforms exploration into a game of cosmic patience, where human operators must trust the invisible lines of gravitational influence to guide their creations through the absolute blackness. The physical vehicles themselves are constructed from lightweight materials designed to withstand extreme thermal variations without fracturing or losing structural integrity. Gold insulation foil, wrapped around delicate instruments, protects them from the intense radiation of the sun, while internal radioisotope thermoelectric generators provide a small, steady trickle of electrical power. This power is used to operate the magnetometers, cameras, and atmospheric sensors that serve as the extended sensory organs of humanity. As these machines drift through the quiet corridors between worlds, their internal systems remain mostly dormant to conserve energy for the critical moments of atmospheric entry or orbital insertion. The human teams remaining on the home planet maintain a quiet vigil, tracking the faint carrier signals that confirm the spacecraft is still functioning as intended. These tracking stations utilize immense parabolic antennas situated in isolated valleys across the globe, ensuring that as Earth rotates, at least one facility remains pointed toward the deep sky. The incoming data arrives not as detailed imagery or clear voices, but as strings of binary code that must be meticulously processed and interpreted by specialized computer algorithms. This slow distillation of knowledge reminds us that space exploration is fundamentally an exercise in listening to the quietest whispers of the universe. The historical transition from tracking nearby planetary bodies to launching the first deep space atmospheric probes marked a significant advancement in our technological capabilities. The Pioneer missions represented an early attempt to cross the formidable boundary of the asteroid belt and gather direct measurements from the outer solar system. These small, spin-stabilized spacecraft were equipped with basic instruments designed to map the interplanetary magnetic field and measure the density of solar wind particles. As they moved further from the Sun, the light that powered previous Earth-orbiting satellites became too weak to sustain scientific operations, necessitating the use of nuclear batteries. The journey through the asteroid belt was initially feared to be a hazardous navigation through dense fields of colliding debris, but the reality proved far more vacant. The vast distances separating individual asteroids meant that the spacecraft experienced an environment of profound emptiness, passing millions of miles away from any major solid bodies. This realization shifted our understanding of the solar system from a crowded celestial arena to a sparse desert where matter is an exceptional rarity. The data returned by these early explorers confirmed that the solar wind extends far beyond the orbit of Mars, creating a massive bubble of charged particles that envelopes the entire planetary system. When Pioneer 10 finally approached Jupiter, it encountered a radiation belt of unexpected intensity, which threatened to overwhelm the delicate electronic circuits within the scientific payload. The spacecraft survived the intense bombardment by a narrow margin, transmitting back the first close-up images of the giant planet and its major Galilean moons. These images revealed a complex system of colored clouds and swirling vortices that challenged the simplistic models previously constructed by Earth-bound astronomers. The success of these missions demonstrated that manufactured instruments could endure the long journeys required to explore the outer reaches of the solar system, opening the door for more ambitious exploratory programs. The subsequent development and execution of the Voyager program transformed our collective perspective on the outer planets and their diverse satellite systems. Voyager 1 and Voyager 2 utilized a rare geometric alignment of the outer worlds that occurs only once every 176 years. This specific arrangement allowed a single spacecraft to visit Jupiter, Saturn, Uranus, and Neptune by using the gravitational field of each planet to increase its velocity and alter its trajectory toward the next destination. This technique, known as a gravity assist, permitted the probes to accomplish in 12 years what would otherwise have required several decades of flight time. The navigation of these twin probes demanded an unprecedented level of precision, as a deviation of just a few kilometers during a planetary flyby would result in a miss of thousands of kilometers at the next target. The flight controllers adjusted the trajectories by firing small thrusters for brief intervals, relying on the calculated laws of physics to guide the machines through the dark. As the spacecraft approached Jupiter, they discovered that the moon Io was home to active volcanic eruptions, which sprayed plumes of sulfur high into the surrounding space. This discovery provided the first evidence of active volcanism on a body other than Earth, completely altering our understanding of tidal heating within satellite systems. The sister moon Europa was revealed to possess a smooth, fractured crust of water ice, hinting at the existence of a deep, global ocean hidden beneath the frozen surface. These findings suggested that the conditions necessary for liquid water and potential habitatic zones were far more widespread than previously assumed. The journey continued onward to Saturn, where the intricate structure of the ring system was mapped in exquisite detail, revealing thousands of individual ringlets shaped by the gravitational influence of small shepherd moons. The probes recorded complex wave patterns and dark spokes moving through the icy structures, indicating that the rings are a dynamic system constantly evolving under the laws of orbital motion. The extension of the Voyager itinerary to the outermost giants, Uranus and Neptune, provided our only close encounters with these remote ice worlds. Voyager 2 arrived at Uranus after a journey lasting nearly 9 years, finding a planet that was uniquely tilted on its side relative to the plane of the solar system. This extreme axial tilt meant that the planet experienced extreme seasonal variations, with its poles pointing directly toward the sun for decades at a time. The atmosphere appeared as a nearly featureless pale blue-green sphere masked by a thick haze of methane gas that absorbs red light. The magnetic field of Uranus was found to be highly unusual, being tilted significantly from the rotational axis and offset from the center of the planet. This asymmetrical magnetic structure created a complex, twisting magnetosphere as the planet rotated through the solar wind. The spacecraft discovered 10 new moons and mapped the dark, narrow rings that surround the planet before using the gravity of Uranus to dive toward Neptune. The arrival at Neptune occurred several years later, revealing a world that was surprisingly dynamic despite receiving very little sunlight to drive its weather systems. The atmosphere featured large, dark storms similar to the Great Red Spot of Jupiter, along with high-altitude clouds of substance that cast shadows on the deeper cloud decks below. The largest moon, Triton, was found to be a frozen world with a retrograding orbit, suggesting it was captured from the outer Kuiper belt long ago. The surface of Triton displayed active geysers erupting nitrogen gas and dark dust into a thin atmosphere, creating dark streaks across the icy plains. This unexpected activity at the very edge of the planetary solar system reinforced the lesson that temperature alone does not dictate geological complexity. After passing Neptune, the spacecraft continued their outward trajectory, heading toward the undefined boundaries where the solar system officially terminates. The investigation of these distant environments required a complete rethinking of how automated systems operate without immediate human intervention. Because the round-trip communication time between Earth and the outer planets can extend to several hours, the spacecraft had to be programmed with autonomous fault protection routines. If a critical system malfunctioned or a sensor recorded an unexpected value, the computer could not wait for instructions from flight controllers on Earth. Instead, it was designed to place the spacecraft into a safe configuration, pointing its main antenna toward the known position of home while attempting to diagnose the issue internally. This level of automation represented a significant milestone in computer science and system engineering, proving that machines could navigate unpredictable environments independently. The survival of these old probes across decades of operation is a testament to the conservative engineering practices of the era, which prioritized durability and redundancy over advanced but unproven technologies. The components were thoroughly tested in vacuum chambers and subjected to intense vibrations to simulate the harsh conditions of a rocket launch. The memory capacity of these onboard computers was incredibly small by modern standards, requiring engineers to write highly optimized code that maximized every single word of digital storage. The data compression algorithms had to be carefully balanced to ensure that important scientific details were not lost during the slow transmission back across the interplanetary gulf. The success of this approach is demonstrated by the fact that both Voyager spacecraft are still communicating with Earth, providing data about the environment outside our solar system. The continuous movement of these metallic messengers across the interstellar boundary provides an opportunity to reflect on the nature of our technological legacy. Long after the structures on Earth have changed and the current generation of researchers has passed away, these machines will continue their silent journeys through the galaxy. To preserve a record of their creators, both Voyager probes carry a golden record containing sounds, images, and greetings from the people of Earth. These copper discs are coated in gold and enclosed in protective aluminum jackets, designed to survive for billions of years in the stable environment of deep space. The records include recordings of wind, rain, animal calls, and musical compositions from diverse cultures across human history, along with diagrams explaining our location in the galaxy relative to known pulsars. This symbolic message is not intended for a specific recipient, but serves as a quiet testament to a species that once looked up at the stars and wondered about its place in the cosmos. The probability of these small objects ever being intercepted by another civilization is incredibly low, given the immense scale and emptiness of interstellar space. They are destined to become artificial comets, orbiting the center of the Milky Way galaxy every few 100 million years, without ever approaching another star system closely. This reality highlights the dual nature of our space exploration efforts, which are simultaneously acts of precise scientific inquiry and expressions of human curiosity. We construct these complex machines to solve specific equations about planetary atmospheres, but in doing so, we also create enduring monuments that outlast our own civilization. The ongoing management of these distant assets requires a dedicated team of engineers who specialize in maintaining ancient technology. The individuals who currently operate the Voyager spacecraft must understand programming languages and hardware configurations that were designed in the mid-20th century. They read through yellowed paper manuals and consult archival documentation to understand how the internal systems react to changing conditions. As the onboard nuclear power supplies continue to diminish, the engineering team must make difficult decisions about which scientific instruments to turn off to preserve the core functionality of the vehicle. One by one, the heaters and sensors are deactivated, allowing individual components to freeze in the cold dark while the main computer continues to run. This gradual winding down of the mission is a slow, dignified process that mirrors the aging of the humans who built and managed the project over generations. The data received from the edge of the solar system becomes more sparse as the signal strength declines, requiring longer integration times at the ground stations to separate the engineering data from the background noise of the universe. Despite these challenges, the information gathered remains invaluable, as it provides our only in situ measurements of the region where the solar wind meets the interstellar medium. The boundary is not a sharp line, but a turbulent region where particles from our sun slow down and interact with the ancient material flowing between the stars. The exploration of this outer boundary reminds us that our solar system is not isolated from the rest of the galaxy, but is deeply connected to the wider cosmic environment. The interstellar wind that blows past our planetary system contains the remnants of supernovas that occurred long before our sun was born, carrying the heavy elements that eventually formed our own planet. By measuring the composition and velocity of these particles, our instruments help us reconstruct the history of our stellar neighborhood. This understanding provides a sense of continuity that spans across vast distances and deep time, linking the local chemistry of our home world to the grand cycles of galactic evolution. The slow pace of these missions encourages a reflective perspective, where progress is measured not in days or weeks, but in decades of continuous observation. This steady accumulation of data allows scientists to build a comprehensive picture of the environment that surrounds us, reducing the uncertainty that once dominated our view of the deep cosmos. The persistence of these old machines serves as a reminder that meaningful exploration requires a commitment that extends beyond short-term goals, demanding a patient investment in the future of human knowledge. The space between the stars is not completely empty, but contains a low-density mixture of gas and dust that forms the interstellar medium. As our probes move deeper into this region, they experience a different set of physical conditions than those found within the protective bubble of the heliosphere. The cosmic ray intensity increases as these high-energy particles are no longer deflected by the solar magnetic field, presenting a different environment for the delicate electronic components. The tracking of these changes allows physicists to refine their models of cosmic ray acceleration and understand how these particles influence the atmospheres of outer worlds. The data gathered by these solitary instruments represents the absolute frontier of human exploration, marking the furthest extent to which our species has extended its sensory reach into the universe. The knowledge we gain from these distant perspectives forces us to confront our own smallness, as the entirety of human history appears as a brief moment occurring on a tiny speck of dust suspended in a vast, dark arena. This realization is not discouraging, but instead offers a profound sense of quietude, allowing us to see our local concerns in the context of an enduring and magnificent cosmic order. We continue to listen to the faint signals as long as they persist, accepting that eventually the silence will become absolute. The slow dissolution of our connection with these outer probes is a natural conclusion to a journey that began with the earliest astronomical observations. The human desire to understand what lies beyond the horizon has driven the development of technologies that allow us to step away from our origin point. From the simple optical lenses used by early astronomers to the nuclear-powered instruments drifting through interstellar space, our methods have become more sophisticated, but the underlying motivation remains unchanged. We are driven by a quiet need to observe, to document, and to understand the mechanisms that govern the universe we inhabit. This process requires an acceptance of the vast scales involved, recognizing that our individual lifetimes are insufficient to witness the complete journey of our machines. We build them, launch them into the night, and hand over the responsibility of monitoring them to future generations, creating a chain of human effort that spans across decades. This collaborative continuity is what allows us to achieve a presence in the deep cosmos, transforming our brief existence into a lasting contribution to the map of the known universe. As we look out into the dark sky, we can be confident that our small metallic emissaries are still moving forward, carrying our history into the infinite silence of the stars. The earliest robotic missions targeted our closest neighbor, the shrouded planet Venus, which sits closer to the Sun. Scientists initially theorized that beneath its thick, impenetrable layers of white cloud might lie a warm, swampy world similar to prehistoric Earth. In the mid-20th century, a series of planetary probes attempted to pierce that dense atmosphere to discover what lay hidden on the ground below. When the first instruments successfully descended through the atmosphere, they recorded an environment that was entirely unexpected. The atmospheric pressure was found to be nearly 90 times greater than that of Earth, creating a crushing weight equivalent to being deep underwater. The temperature on the surface was high enough to melt lead, caused by a runaway greenhouse effect that trapped the solar heat. The robotic landers sent to the surface managed to survive for only a few hours before the intense heat and pressure permanently silenced their internal electronics. In those final moments, they transmitted precious, grainy images of a flat, orange landscape baked in perpetual twilight under a choking sky. We learned that Venus was not a lush tropical world, but a stark reminder of how planetary climates can diverge into extreme environments. There is still much that remains unresolved about the internal geological activity of Venus and whether its ancient past held liquid oceans. Astronomers continue to analyze the sparse radar data, accepting that our knowledge of this pressurized world remains incomplete and obscured by its toxic clouds. To understand the wider context of our solar system, we must look further outward to the red plains of Mars. This dry desert world has attracted our attention for centuries because its surface features can be observed directly through telescopic lenses from Earth. Early flyby missions eliminated the old romantic myths of engineered canals, revealing instead a cold, cratered surface that closely resembled our own moon. Subsequent orbiters and rolling robotic rovers discovered extensive evidence of ancient valleys and dried riverbeds carved deep into the rusted soil. The data indicated that liquid water once flowed across the surface billions of years ago. suggesting a much warmer and thicker atmosphere in the distant past. Yet, current instruments show a world that is now frozen and dry, with a thin atmosphere composed mostly of carbon dioxide. The mysterious disappearance of the Martian magnetic field long ago allowed the solar wind to slowly strip away the planet's protective atmospheric blanket over deep time. The ultimate fate of that ancient Martian water remains an open question, with much of it likely locked away as deep ice beneath the dusty ground. Scientists patiently study the chemical composition of the soil, comfortable with the uncertainty of whether microscopic life ever existed in those ancient, vanished lakes. Let us move outward, beyond the rocky inner planets, into the immense asteroid belt that separates them from the outer giants. This region is populated by millions of fragments of rock and metal left over from the initial formation of our solar system. Now let's slowly expand outward. One level beyond our own solar system lies the Milky Way, our home galaxy. To a human, the Milky Way is unimaginably large. It contains hundreds of billions of stars, each perhaps holding its own family of planets. If our solar system were the size of a single grain of sand, the Milky Way would be the size of a large city. It takes light, the fastest thing in the universe, about 100,000 years, just to cross from one side of our galaxy to the other. Scientists understand the Milky Way by observing the way its stars orbit a common center, a quiet, swirling dance of gravity that has been repeating for over 13 billion years. What we know so far suggests that we are a typical spiral galaxy, a beautiful, orderly structure of gas and dust. But even with everything we've learned, there are still things we don't fully understand about our own home. We see hints of dark matter holding the edges together, acting like an invisible scaffolding we cannot touch. Not because we're missing something urgent, but because the universe moves slowly and we have only been watching for a heartbeat of cosmic time. And for now, that uncertainty is simply part of the picture. It doesn't need to be resolved tonight. With that in mind, let's move outward once more to an even larger scale. Ga, Ga, Ga. To truly understand the Titan that is IC 1101, we must first linger for a moment in the foyer of our own home, the Milky Way. When we look up at a dark sky, we see a misty river of light flowing across the heavens. To the ancient Greeks, it was spilled milk. To others, a celestial path. Scientifically, we know it as a barred, spiral galaxy, a swirling disk of dust, gas, and at least 200 billion stars. Our sun is just one of those stars, tucked away in a quiet suburb known as the Orion Arm. We are roughly 26,000 light years from the bright, crowded center, spinning at a comfortable pace that takes 230 million years to complete a single orbit. The last time we were in this exact spot in space, dinosaurs were only just beginning to walk the Earth. This is the rhythm of the local neighborhood. It is a slow, majestic carousel. We think of our galaxy as massive, and in human terms, it is. If you were to try and count every star in the Milky Way, 1 star per second, you would be counting for nearly 7,000 years. It is a number that exceeds the span of recorded human history. And yet, when we compare this to the largest galaxy ever found, the Milky Way begins to feel like a small, cozy village. Our home spans about 100,000 light years. It is a vast distance, one that light the swiftest messenger takes a millennium of centuries to cross. But the universe is a ladder of scales, and we are currently standing on one of the bottom rungs. Scientists understand the Milky Way by observing the motion of the stars near its heart. There, stars move with a frantic, hidden energy, orbiting a central point of immense gravity. This is Sagittarius A*, a supermassive black hole. It is the anchor of our galaxy, a dark sun around which all else revolves. Yet, despite its power, it represents only a tiny fraction of the galaxy's total mass. The rest of the mass is a mystery. When we measure how fast the stars at the outer edges are moving, they seem to be moving too fast. By all the laws of visible matter, they should be flying off into the void, like water droplets spun from a wet cloth. But they stay. They are held by an invisible hand. This is the invisible scaffolding mentioned before dark matter. We cannot see it, we cannot taste it, and it passes through your body right now without leaving a trace. It is a ghost that holds the stars in place. It makes up the vast majority of our neighborhood's weight, yet it remains silent. Scientists estimate that for every gram of normal matter, the stuff that makes up trees, oceans, and your own heartbeat, there are 5 grams of this mysterious substance. We are like children looking at a magnificent building and only seeing the windows, unaware of the steel beams behind the glass. But there is no tension in this mystery. The Milky Way has been held together by this invisible support for over 13 billion years. It is not going anywhere. It is a stable, maturing structure. We see other galaxies in our local group, like the Andromeda Galaxy, which is currently drifting toward us at 250,000 miles per hour. Even at that speed, the collision won't happen for another 4 billion years. The universe is so empty that when our 2 galaxies eventually merge, the stars themselves will likely never touch. They will simply pass by each other like ghosts in a hallway, eventually settling into a new, larger arrangement. The Milky Way is a place of constant, quiet recycling. In the cold clouds of gas and dust between the stars, gravity is always at work. It pulls the dust together until it grows hot and dense, eventually igniting into a new star. When those stars die, they exhale their elements back into the void: carbon, oxygen, iron, the very ingredients that eventually formed the Earth and everything on it. We are literally made of the recycled breaths of ancient stars in this local neighborhood. It is a closed system of cosmic elegance. However, as we look further out, we realize that the Milky Way is part of a small, relatively lonely cluster called the local group. We have a few dozen neighbors, most of them small dwarf galaxies that look like tattered clouds. We are the big fish in a small pond. But if we were to travel toward the constellation of Virgo, or further still toward Serpens, the density of the universe begins to change. The ponds become lakes, and the lakes become oceans. When we look at the Milky Way from the outside, it is a beautiful, thin disk with graceful arms. It is a fresh galaxy, still forming stars, still vibrant with the blue light of youth in its spiral limbs. It is a place of birth and movement. But the giants we are searching for, the IC 1101s of the deep, have long since moved past this phase. They have stopped the frantic business of star birth. They have become something more singular, more monolithic. Imagine the Milky Way as a single sheet of paper. To represent the scale of the largest galaxy found, you would need to stack thousands of sheets of paper until they reached the height of a tall building. The sheer volume of space occupied by our neighbor is a drop in the bucket compared to the volumes we are about to explore. Our local neighborhood is a sanctuary of sorts, a quiet, predictable corner of the cosmos, where the light of 200 billion suns provides a sense of familiar warmth. But the horizon is calling. Beyond the edges of our dark matter halo, beyond the reach of the Andromeda Galaxy's gravity, lies the Great Attractor and the vast clusters of the Laniakea supercluster. We are moving away from the spiral life, the life of arms and disks, and toward the elliptical life, the life of pure, concentrated mass. In this transition, we leave behind the blue stars and the gas clouds. We move toward a region where the stars are older, redder, and packed together in densities that would make our night sky look like a solid wall of gold. We are moving toward the center of the Abell 2029 cluster. If the Milky Way is a suburban home, the environment around IC 1101 is a sprawling, ancient metropolis that never sleeps, yet never moves. The uncertainty of our own galaxy, the mystery of its dark matter, the exact shape of its hidden arms, serves as a gentle reminder that we are still learning the alphabet of the universe. We are like travelers who have only just stepped out of their front door and are already amazed by the size of the street. But the street leads to a city, and the city leads to a continent. As you settle deeper into your rest, let the Milky Way fade into the background. It is a sturdy home, and it will be here when you wake. Its 230 million year orbit will continue, unbothered and serene. The dark matter will continue to act as its silent guardian, but your mind is now free to drift further. We are crossing the intergalactic void, the vast, empty space where light travels for millions of years without hitting a single atom. It is quiet here, between the galaxies. There is nothing to see, nothing to hear, only the soft expansion of space itself. We are moving toward a light that has been traveling for 1 billion years. It is a pale yellow glow, growing larger and larger until it fills the entire field of vision. This is the light of 1 trillion souls, the light of a galaxy that has forgotten how to be small. With that in mind, let's move outward once more to an even larger scale. As we drift further from the familiar spiral arms of our Milky Way, we enter the great intergalactic desert. This is a place where distance takes on a physical weight. Between our home and the destination we seek, there are stretches of nothing so vast that entire civilizations could rise, reach the stars, and fade into dust without ever crossing the gap. In this space, the atoms are so few that you could travel for 1,000 years and never encounter a single grain of matter. It is a vacuum of such purity that it makes the air in your room feel like a dense, heavy liquid. Here, in the profound stillness of the local neighborhood's edge, we begin to realize that the universe is not made of objects, but of the space that holds them. To understand the journey we are taking, we must look back at our own cluster, the local group. It is a small, intimate collection of galaxies. The Milky Way and Andromeda are the two anchors, spinning around each other in a slow, multi-billion-year embrace. Around us are the stragglers, the Magellanic Clouds, the Triangulum Galaxy, and dozens of dwarf galaxies that look like tattered scraps of silk. This is our porch. It is a cozy corner of the cosmos. But as we move outward, the neighborhood begins to change. The gaps between the stars are replaced by the gaps between the galaxies. We are leaving the era of the individual sun and entering the era of the collective glow. Imagine the time it takes for a message to travel across this neighborhood. If you were to send a beam of light from one side of the local group to the other, it would take nearly 10 million years to arrive. Any news we receive from our neighbors is ancient by the time it reaches our eyes. We are looking at a history book written in the language of photons, and there is a deep intellectual comfort in this delay. It means that nothing in the universe happens suddenly. Everything has a long lead time. The light of the giant galaxy IC 1101, which we are now approaching, has been traveling toward us since before the first mountains on Earth were raised toward the sky. It is a light that has seen the birth of every creature that ever walked the ground beneath you. As we move further out, the individual stars of the Milky Way merge into a single, faint smudge of light behind us. Our sun is no longer visible. Our planets are gone. The entire history of humanity is contained within a speck of light that is slowly vanishing into the distance. This challenges how we think about our own importance, but it does not diminish us. Instead, it expands us. We are the consciousness that has traveled this far. We are the part of the universe that is looking back at the porch we just left. There is no urgency to return. The local neighborhood is safe. It is held in the same laws of physics that govern the giant we are about to meet. Scientists observe these distant scales by using gravitational lenses, places where the mass of a cluster is so great that it bends the light from even more distant objects, like a cosmic magnifying glass. It is as if the universe is helping us to see it. It is providing the tools for its own discovery. This suggests a sense of cosmic continuity, a feeling that the universe is not just a random collection of things, but a coherent system that wants to be understood. As we move outward, we are not moving into chaos. We are moving into a more complex form of order. The light of IC 1101 is now a dominant presence in our field of vision. It is no longer a smudge. It is a sprawling, golden continent of light. It is an elliptical giant, a structure that has moved past the frantic starbirth phase of our own neighborhood and into a state of graceful endurance. While the Milky Way is still working, busy making new stars and recycling gas, IC 1101 has finished its labor. It is a place of rest. Its trillions of stars are old, steady, and red. They move in paths that are millions of light years long. To a star in this galaxy, 1 billion years is just a season. But even with our best telescopes, there are things about this transition that remain accepted unknowns. We don't fully understand the warm, hot, intergalactic medium, the thin, invisible gas that lingers between the clusters. It is so hot that it should be glowing brightly, yet it is so thin that it is almost impossible to detect. It is a ghost of the early universe, a remnant of the fire that started it all. For now, that uncertainty is simply part of the picture. We don't need to measure every atom to feel the warmth of the cosmic breath. We can simply exist in the space between the explanations. As you drift deeper into the night, imagine yourself floating in that intergalactic void. You are halfway between our local neighborhood and the giant galaxy. Behind you is the familiar glow of home. Ahead of you is the golden orb of the deep. You are in the most peaceful place in existence. There is no gravity here to pull you down, no atmosphere to limit your vision. You are a point of awareness in a sea of infinite space. The expansion of the universe is carrying you gently forward, a silent current that moves without effort. Over immense spans of time, the light of the trillion souls in IC 1101 will wash over you. It is a light that has been purified by its journey through the void. It is a light that has lost all its shadows. In the heart of the largest galaxy, there are no dark corners. Everything is illuminated by the soft, amber radiance of ancient suns. This is the goal of our expansion, to move from the small, shadowed world of the local neighborhood into the broad, unshadowed light of the cosmic giants. With that in mind, let's move outward once more, to an even larger scale. We are leaving the porch and entering the city. We are moving from the familiar stars to the structures that hold the stars. The universe is getting larger, and we are getting quieter. There is no rush. The light has been traveling for 1 billion years. It can wait for us to drift into its embrace. The steady, unceasing flow of time and space is the only thing that matters now. The numbers are fading. The distances are merging. There is only the light, the yellow glow of 1 trillion suns, waiting to tell us the rest of the story. Welcome to the grand theatre of the cosmos. Across the vast expanse of time and space, there exists a narrative that surpasses all others in scale and complexity. It is the story of everything that has ever been and everything that will ever be. Tonight, we turn our gaze upward to the infinite velvet dark to explore the fundamental forces and celestial bodies that define our existence. This journey begins not on a distant star, but right here on the blue marble we call home. Humanity has always been a species of explorers, driven by an innate curiosity to understand the lights that dance above us. From the primitive star charts drawn in caves to the sophisticated orbital observatories of the modern era, our quest for knowledge has been relentless. Consider the history of those who first dared to map the heavens. Ancient civilizations looked at the same constellations we see today and wove them into the fabric of their mythologies, creating stories that served as both guidance and philosophy. Yet, the transition from myth to science marked the true dawn of our understanding. Think of the pioneers like Galileo Galilei, who turned a crude spyglass toward the moon and forever shattered the notion that the heavens were perfect and unchanging. His courage to observe and report what he saw, despite the immense social and political pressure of his time, remains a guiding principle for every astronomer today. We stand on the shoulders of these intellectual giants, using the principles of physics they helped define to unravel the mysteries of the universe. The cosmos is a realm governed by strict physical laws, yet it remains profoundly mysterious. When we discuss the nature of our universe, we must speak of gravity, the invisible architect of all things. It is gravity that pulls dust and gas together to form the first stars, and it is gravity that dictates the orbital dances of planets and moons around their host stars. In the heart of many galaxies lie the most extreme manifestations of this force, known as black holes. These objects are regions of space where gravity is so intense that nothing, not even light itself, can escape their grasp. They are not merely destructive voids, but essential components that shape the evolution of the galaxies they inhabit. The study of black holes challenges our understanding of reality, forcing us to reconcile the predictable laws of classical physics with the strange behavior of matter near the event horizon. To observe these phenomena, we have moved beyond the limits of human eyes. We have built monumental facilities designed to peer deeper into the fabric of space and time. Agencies around the globe now coordinate massive engineering feats, constructing telescopes that act as time machines. By capturing light that has traveled for billions of years, these instruments allow us to witness the universe in its infancy. The James Webb Space Telescope is perhaps the most significant achievement in this endeavor. Designed to observe the infrared spectrum, it pierces through the dense clouds of interstellar dust that once hid the birth of stars and planetary systems from our view. Each image captured by this observatory is a dataset that refines our models of galaxy formation and chemical evolution. Consider the complexity of our own solar system. It is a diverse neighborhood of planets, moons, asteroids, and comets, each telling a unique story of formation and change. We have sent robotic emissaries, our rovers, to traverse the desolate and fascinating surface of Mars. These machines are the robotic pioneers of our time, drilling into rock and analyzing soil to search for signs of past life and to understand the geological history of a world that was once far more active than it is today. Every transmission sent back from these rovers is a triumph of engineering and a testament to the persistent human drive to seek out the unknown. They operate in harsh conditions, powered by the sun and steered by researchers who feel the weight of every command sent across the millions of miles of vacuum. The science of cosmology addresses the biggest questions of all. How did the universe begin, and how will it end? Current evidence points to a colossal expansion that began roughly 13.8 billion years ago. Since that moment, the universe has been growing and cooling, allowing for the formation of the complex structures we observe today. We live in an era where we can measure the cosmic microwave background, the afterglow of the Big Bang, which provides a snapshot of the universe when it was only a few 100,000 years old. This, combined with our observations of dark matter and dark energy, suggests that we see only a small fraction of what actually constitutes the cosmos. The vast majority of our universe is made of components we cannot directly perceive, yet we know they exist by the way they influence the movement of galaxies. The collaborative nature of modern astronomy cannot be overstated. It is a global endeavor that transcends borders, languages, and political divides. When we study the life cycle of stars, we are observing the factories that created the very atoms that make up our own bodies. Every carbon atom, every oxygen molecule, and every trace of iron in our blood was forged in the hearts of stars that died long before our solar system was even a glimmer in the cosmic dust. We are, quite literally, made of star stuff. This realization connects us to the history of the universe in a profound way. We are the mechanism by which the universe has become conscious of itself. Think of the technological advancements that have trickled down from our space exploration efforts. The materials science required to protect spacecraft, the complex computer algorithms used to process data from distant reaches of the galaxy, and the breakthroughs in energy efficiency are all results of the challenges faced when we push the boundaries of what is possible. By attempting to understand the environment of space, we have become better stewards of our own environment here on Earth. The perspective gained from seeing our planet as a fragile blue sphere suspended in an immense dark void has influenced our culture, our politics, and our environmental policies. As we look toward the future, the possibilities are limited only by our imagination and our commitment to exploration. We are planning missions to explore the icy moons of Jupiter and Saturn, where hidden oceans might harbor the conditions necessary for life. We are refining our techniques to detect exoplanets, searching for another world that might share the characteristics of our own. The search for extraterrestrial intelligence continues to evolve as we listen for signals from across the interstellar divide. Even if we find that we are alone, the search itself is worth the effort, for it teaches us more about the uniqueness and the value of the life we have already found. The beauty of the universe is not just in its vastness, but in its mathematical elegance. The patterns we see in the spiral arms of a galaxy are reflected in the growth of biological structures on Earth. The laws of motion that govern a planet in its orbit are the same laws that dictate the trajectory of a falling apple. This interconnectedness is the foundation of physics, the language that allows us to translate the silence of the stars into a coherent story. We are not separate from the universe. We are a vibrant, active, and curious part of it. As we continue this exploration, we must always remember the importance of fundamental research. Much of what we know today began as theoretical curiosity, a question asked by a scientist who wondered why things worked the way they did. The transition from theoretical wonder to technological application is the engine of human progress. When we invest in astronomy and space physics, we are investing in the expansion of human knowledge, which is the most valuable commodity we possess. The challenges are undeniably great. The distances are unfathomable, the conditions are hostile, and the timescales are beyond the capacity of human experience to truly comprehend. Yet, we persist. We build better telescopes, we design faster rockets, and we train the next generation of scientists to take up the mantle. There is a sense of wonder in knowing that there is so much left to discover. The universe is not a closed book. It is an open exploration that rewards the curious and the patient. Consider the role of the modern astronomer. They are no longer just people looking through eyepieces. They are data scientists, engineers, and visionaries who work with vast arrays of sensors and computer networks. They navigate the complexities of international cooperation to ensure that the findings of one are shared with all. This spirit of sharing is the heartbeat of science. It is why we can speak of these things today, and why we can look forward with anticipation to the discoveries that will be announced tomorrow. In concluding this reflection on our place in the cosmos, consider the responsibility we hold. We are the current witnesses to the history of the universe. We have the capability to look back in time and the technology to project our reach into the future. Whether we are studying the formation of planets, the cooling of white dwarfs, or the expansion of the dark energy that permeates the void, we are engaging in the most noble of human endeavors. We are seeking to understand the truth of our origins and the nature of our destiny. So, let us keep our eyes on the stars. Let us continue to support the agencies and the individuals who dedicate their lives to exploring the unknown. The next great discovery might be just beyond the next horizon, hidden in the data of a telescope or revealed by the sensors of a probe. The universe is waiting to be understood, and we are ready to listen to its story. Through our combined efforts, through the relentless application of logic and the burning flame of curiosity, we will continue to push back the boundaries of the dark and fill the map of the unknown with the light of knowledge. This is the enduring legacy of the human spirit, a spirit that refuses to be confined to the ground, a spirit that insists on reaching for the heavens to find its true place among the stars. The journey is far from over, and the best parts of the story are yet to be written. Everything that we have discussed, from the smallest particle in a laboratory to the largest structure in the universe, is part of one singular, grand, and beautiful process. It is a process that we are honored to participate in and privileged to understand. May our pursuit of this understanding never cease, for in the light of the stars, we find the reflection of ourselves. The chronicle of our exploration continues, pushing deeper into the tapestry of the night sky, where the rules of the macrocosm unfold in grand displays of energy and matter. When we contemplate the life cycle of stars, we are witnessing a narrative of birth, maturity, and inevitable transformation. From the vast, cold clouds of molecular gas that collapse under their own gravity to the violent, brilliant supernovae that seed the galaxy with heavy elements, the process is one of constant renewal. Each star acts as a cosmic furnace, synthesizing elements in its core through the process of nuclear fusion, balancing the inward pull of gravity against the outward pressure of radiation. When a massive star reaches the end of its lifespan, it undergoes a spectacular collapse, creating the elements essential for life and scattering them across the interstellar medium, which will eventually form the next generation of stars and planetary systems. This cycle is the fundamental mechanism of chemical evolution, turning the simple hydrogen and helium born in the first minutes of the universe into the complex chemistry that allows for life to emerge. Beyond the stars, we turn our attention to the structure of galaxies themselves. Whether they are spiraling disks adorned with glowing dust lanes and clusters of young blue stars, or elliptical collections of ancient red stars, each galaxy is a gravitationally bound city of billions of individual suns. Our own Milky Way is a barred spiral, a massive entity that houses our solar system in one of its quieter suburbs. Understanding how these massive structures grow and interact requires us to look at the large-scale architecture of the universe, where galaxies are organized into clusters and superclusters, connected by filaments of dark matter that form the cosmic web. This web is the scaffolding upon which the visible matter of the universe is hung, and mapping it is one of the primary goals of modern observational cosmology. Consider the role of dedicated space observatories in mapping this web. Telescopes, such as the Hubble Space Telescope, have provided us with iconic views of distant galaxies, allowing us to estimate the age of the universe with remarkable precision. By measuring the recession velocity of these galaxies and their distance from us, astronomers have been able to confirm the expansion of space itself. This expansion is not merely galaxies moving apart through static space, but the stretching of the very fabric of space and time. Furthermore, the discovery that this expansion is accelerating has led to the inclusion of dark energy in our cosmological models. Dark energy, an enigmatic force that seems to act as a repulsive pressure, dominates the energy budget of the universe. While its exact nature remains one of the greatest unsolved problems in physics, its presence determines the ultimate fate of everything we see. The study of planets, both within our solar system and beyond, offers a different perspective on our place in the universe. Within our neighborhood, the diversity is startling. We have rocky inner planets with active volcanoes and tectonic plates, and gas giants that function as miniature solar systems with their own complex moons. Exploring these worlds is a matter of planetary science, a field that uses the data from orbiters and landers to reconstruct the history of environmental conditions across billions of years. We look for evidence of past liquid water, for signs of geological activity, and for the chemical precursors that might suggest an environment conducive to life. Each discovery on Mars, on Europa, or on Enceladus recalibrates our understanding of how unique, or perhaps how common, the conditions for life might be. When we look beyond the solar system to exoplanets, we enter the realm of statistics and atmospheric analysis. By observing the slight dimming of a star as a planet transits in front of it, or measuring the subtle gravitational wobble of a star induced by an orbiting companion, we have confirmed the existence of thousands of worlds. Some are scorched giants orbiting perilously close to their host stars, while others reside in the habitable zone, where temperatures might allow for liquid water on the surface. Future missions are being designed to perform spectroscopy on the atmospheres of these distant worlds, seeking signatures of oxygen, methane, and other gases that could indicate biological activity. This is the search for life at a truly interstellar scale, a project that bridges the gap between planetary science and biology. Let us also acknowledge the scientists who spend their lives refining these theories. The work of an astronomer is not limited to observation. It is deeply rooted in the rigorous application of mathematical models and computational simulations. Using supercomputers, theorists model the complex dynamics of gas, the gravitational interactions of thousands of bodies, and the influence of magnetic fields on plasma. These simulations allow us to test hypotheses that would be impossible to verify in a laboratory setting. They enable us to see how a galaxy evolves over billions of years, or how a black hole tears apart a passing star. The synergy between observation and simulation is what drives the progress of modern science. It allows us to move from simply cataloging the contents of the universe to understanding the underlying mechanisms that create them. Historical perspective reminds us that our current understanding is only the most recent chapter. The transition from the geocentric view, where everything orbited the Earth, to the heliocentric model was a revolution that changed humanity's self-perception. Today, we are undergoing a similar shift, moving from a view of a static universe to one that is dynamic, expanding, and composed mostly of components we do not yet understand. This journey of discovery is marked by monumental technical hurdles. From the challenges of atmospheric interference that necessitated the launch of space telescopes, to the extreme engineering required to keep rovers operating on a freezing Martian surface, the history of space exploration is a history of overcoming the impossible through human ingenuity. Consider the international collaboration that defines the current era. Major facilities are rarely the work of a single nation alone. They represent the combined efforts of thousands of engineers, scientists, and technicians from around the world. These projects foster peace and cooperation, providing a common goal that transcends cultural and political differences. When we share the data from a satellite or a ground-based array, we are contributing to a global pool of knowledge that benefits all of humanity. This spirit of cooperation is essential, as the challenges of the future, such as the construction of permanent lunar bases or the long-term exploration of the outer solar system, will require resources and expertise that no single entity can provide on its own. We must also appreciate the sheer scale of the challenges posed by the universe. Radiation, vacuum, extreme temperatures, and the vast distances between stars make space an inherently hostile environment. Yet, it is this very hostility that drives innovation. Every material developed to withstand the heat of re-entry, every sensor designed to operate in the intense radiation environment of Jupiter, and every power management system built to run on the thin energy of a distant sun represents a breakthrough that improves technology here on Earth. Space exploration is a crucible for progress, pushing us to solve problems that we did not even know we had. The philosophical implications of our findings are equally profound. Knowing that we live in a universe governed by consistent physical laws, from the scale of the atom to the scale of the galaxy, gives us a sense of belonging. We are part of a rational, ordered system that can be studied and understood. This does not diminish the mystery or the beauty of the cosmos. Rather, it enhances it. The more we know about how the universe works, the more we can appreciate the complexity and the elegance of the phenomena we observe. From the way light bends around a massive object to the way a star dies, everything follows a path defined by the fundamental forces of nature. As we continue to advance, we must prioritize the cultivation of curiosity in the next generation. The scientists and engineers of tomorrow are currently in classrooms, looking at images of the cosmos and wondering how it all works. Providing them with the tools, the education, and the inspiration to pursue these questions is the best investment we can make. We must share the stories of our failures and our successes, showing that science is not just a collection of facts, but a process of questioning, experimenting, and refining our models of reality. It is a process that requires resilience, skepticism, and, above all, a deep, abiding wonder. Think of the dark skies away from city lights, where the band of the Milky Way is clearly visible. That view has been the constant companion of humanity throughout our history. It has inspired poets, philosophers, and scientists alike. In those moments of quiet contemplation, we are reminded that we are small, yet we are capable of understanding the vastness that surrounds us. That is the true miracle of our existence. We are the universe observing itself, questioning itself, and seeking to understand its own origin. This realization brings with it a sense of stewardship. We have only one home planet, and as we look out into the void, we are reminded of how rare and precious the conditions on Earth truly are. The future of astronomy and space science is limited only by our willingness to explore. Whether we are launching the next generation of space telescopes that will look back even further in time, or deploying robotic fleets to map the asteroids that could provide the resources for further expansion, we are constantly expanding our reach. The data we collect today will be the foundation for the theories of tomorrow. We are laying the groundwork for a future where humanity is not just a spectator of the cosmos, but a participant. A future where we understand not just what the universe is, but how we fit into its long and complicated history. In concluding this exploration, let us reflect on the enduring nature of our quest. We started with the primitive observation of the heavens, and we have moved to the sophisticated analysis of cosmic radiation, black holes, and the accelerating expansion of space. Each step has brought us closer to the truth, and each step has revealed that the universe is far more complex and interesting than we could have imagined. There is no finish line in science. There is only the continuous process of asking better questions and finding more precise answers. The darkness of space is not a void to be feared. It is a canvas upon which we are painting the picture of our understanding. Let us remain steadfast in our dedication to this noble pursuit. Let us continue to look up with wonder and to build with purpose. The universe is patient, and it will continue to reveal its secrets to those who have the courage to ask and the persistence to seek. From the smallest subatomic particles to the largest clusters of galaxies, the entire story of the universe is written in the language of physics, and it is a story that we are slowly, patiently learning to read. We are the explorers of the infinite, and our journey has only just begun. The beauty of the stars, the mystery of the deep space, and the promise of discovery are waiting for us. All we have to do is keep looking up, keep learning, and keep reaching for the vast potential that lies among the stars. Our history is a testament to what we can achieve when we work together, and our future is a blank page waiting for the discoveries that will define the next great era of human exploration. The stars are calling, and we are finally learning how to answer. In the end, we will find that we are connected to every part of the cosmos, from the atoms in our cells to the light of the most distant quasar. We are all part of one grand, magnificent, and eternal design that continues to unfold before our very eyes. We have the privilege of witnessing this, of analyzing it, and of sharing it, and that is a responsibility that we must carry forward with pride and determination. Our quest for knowledge is the defining characteristic of our species, and it is the key that will unlock the mysteries of the universe, one observation at a time. May we always be guided by the light of discovery, and may our collective spirit continue to drive us toward the horizons that have yet to be explored. The story is ours to tell, and the future is ours to build. Let us continue to explore, to learn, and to grow as we make our mark on the cosmos and find our true place among the infinite lights of the night sky. When we think about size, we often imagine it in human terms. Distances we can walk in an afternoon, the height of a mountain that takes a day to climb, objects we can see with our own eyes, like a cathedral or a sprawling city. For example, if you were to walk consistently without stopping, it would take you about 9 years to walk the circumference of the Earth. That feels like a long time. It represents a significant portion of a human life. But in the context of the universe, the Earth is not an object of size, it is a point of departure. Astronomers often feel like cartographers trying to map an ocean while standing on a single grain of sand. This comparison isn't perfect, but it gives us a calm place to begin. Beyond our atmosphere, the definition of an object begins to change. It stops being something with a hard edge and starts becoming a collection of influences. Now, let's slowly expand outward. Consider, for a moment, the concept of a long journey in your own life. Perhaps it is a drive across a continent where the landscape shifts slowly from green forests to rolling plains. You measure that progress by the hours on a clock, the meals you eat, and the rising and setting of the sun. To us, 1,000 miles is a formidable distance. It is a distance that requires planning, fuel, and time. Yet, if we were to shrink the entire Earth down to the size of a single glass marble, that 1,000-mile journey would be a microscopic scratch on its surface, invisible to the naked eye. We live our entire lives on the skin of this marble, rarely considering the depth of the void that begins just a few miles above our heads. If you were to stand in an open field and look up at a clear night sky, your eyes are reaching out across distances that the human brain isn't quite equipped to process. When you see the moon, you are looking at an object that is about 239,000 miles away. If you could drive a car to the moon at highway speeds, It would take you about 5 or 6 months of continuous driving to get there. No stops for rest, no traffic, just a straight line through the silence. This is our nearest neighbor, a mere stone's throw in the cosmic sense, yet it already exceeds the scale of a human life's daily movement. As we move further, we must leave behind the measurements of miles and kilometers. They become too small, like trying to measure the width of the Atlantic Ocean using a ladybug as a ruler. Instead, we use the speed of light. Light is the fastest thing we know of, traveling at 186,000 miles per second. In the time it takes you to blink, light has already circled the Earth 7 times. It is a speed so fundamental that it sets the pace for the entire universe. And yet, even at this impossible speed, the universe is so vast that light itself takes time to get anywhere. When you look at the moon, you are seeing it as it was 1.3 seconds ago. You are already looking into the past, if only by a moment. To understand the largest structures in existence, we have to get comfortable with this idea of light time. Think of it as a cosmic delay. The further out we look, the further back in time we see. It is a gentle, natural form of time travel. If the sun were to suddenly go out, we wouldn't know for 8 minutes. For those 8 minutes, we would continue to feel its warmth and see its light, living in a beautiful, lingering echo of something that is already gone. This realization isn't meant to be unsettling. It is meant to show you how the universe buffers us from its true scale. We are tucked away in a quiet corner of time and space, shielded by the sheer slowness of information. Imagine walking through a vast, silent forest at twilight. You can see the trees immediately around you with great detail, the texture of the bark, the shape of the leaves. But as you look further away, the trees become silhouettes, and eventually they blend into a soft, indistinct grey haze. The universe is much like this forest. Near us, we see individual planets and stars. But as we expand our perspective, those individuals begin to group together. They become part of something larger, something more diffuse. We often think of objects as things made of solid matter, a rock, a house, a mountain. But as we move into the human-scale perspective of the cosmos, we see that objects are often mostly empty space. If you were to take an atom, the building block of everything you see, and blow it up to the size of a football stadium, the nucleus would be like a small marble in the center, and the electrons would be like tiny gnats buzzing around the very highest seats in the stands. Everything in between is nothing, emptiness. To you, the chair you are sitting on, and the planet beneath you are made almost entirely of this nothingness, held together by invisible forces. This same principle applies to the stars and galaxies. If we imagine our galaxy, the Milky Way, as a vast city, the stars are like individual streetlights. From a distance, the city looks like a solid glow of light, a single object of immense proportions. But as you move inside, you realize the streetlights are blocks, even miles apart. There is a great deal of dark, quiet space between them. When we talk about the largest object, we are talking about a structure that is made of billions of these cities, all arranged in a way that suggests a grand, hidden order. Scientists spend decades trying to find the edges of these structures. They use massive telescopes that act like buckets, slowly collecting the faint, tired photons of light that have been traveling for millions of years just to reach us. What they find is that the universe isn't just a random collection of things thrown into a box. It has a texture, it has a shape, it looks like a web, or perhaps the neurons in a brain, or the foam on top of a cup of coffee. It is a collection of filaments and voids where the objects are so big that they define the very curvature of space itself. As you lie there, let the scale of this begin to wash over you. You are a part of this structure. The atoms in your body were forged in the hearts of stars that lived and died billions of years ago. You are a way for the universe to look back at itself and wonder about its own size. There is no need to feel overwhelmed. Just as a single cell in your body doesn't need to understand the complexity of your entire life to do its job, you don't need to grasp the 93 billion light years of the observable universe to be a part of it. You are anchored here on this 9-year walk-wide marble, safe and still. We are about to step off this marble and begin the climb. We will move through the solar system, past the giants of gas and ice, and out into the interstellar dark. We will see things that defy the imagination, but we will do so with the same calm, rhythmic pace. The universe is patient. It has been expanding for 13.8 billion years, and it is in no hurry to finish. Now, let us take that first step away from the familiar. Let us leave the lights of Earth behind and look toward the sun, our local anchor and the first true giant in our path. To understand the vastness of the largest objects ever discovered, we must first reconcile our own physical presence with the immediate neighborhood of our star. We often think of our world as a massive, solid foundation, a place of continents and oceans that take days to cross by air and weeks by sea. But as we elevate our perspective, the Earth begins to shrink, transitioning from a world of infinite variety into a singular, fragile marble of blue and white, suspended in a velvet dark that is deeper than any night you have ever experienced on the ground. Consider the distance between your home and the Sunday. It is approximately 93 million miles. To a human mind, 93 million of anything is an abstraction, a number that sits on a page without a physical weight. But let us try to feel that distance. If you were to board a commercial jet and fly toward the sun at a constant cruising speed, you would not arrive for 19 years. You would spend nearly 2 decades in the air, crossing a silent, airless gulf just to reach the nearest star. This is the scale of our local backyard. It is a distance that defines the boundaries of our biological reality, yet in the cosmic census, it is a microscopic gap. The sun itself is the first true lesson in the universe's love for the gargantuan. It is a sphere of glowing plasma, so immense that if it were hollow, you could pour 1,300,000 Earths into it. Imagine a large glass jar filled with tiny grains of sand. Each grain is an entire world, with its own history, its own mountains, and its own billions of people, all rattling around in the bottom of a container that represents a single, average star. This comparison isn't meant to diminish the Earth, but to provide a calm place to begin our ascent. When we speak of the largest objects in the universe, we are moving towards structures that make our sun look like one of those grains of sand. Scientists understand the sun by observing its heartbeat, the way it pulses with magnetic energy and sheds its outer layers in a constant solar wind. This wind creates a bubble around us, a protective shield called the heliosphere. This is the first object we encounter that lacks a solid surface. It is a structure made of pressure, particles, and light. It reminds us that as we move outward, the definition of an object begins to change. It stops being something you can touch and starts becoming a collection of influences. The sun is not just a ball of fire, it is a gravitational anchor that holds the solar system in a steady, rhythmic dance, ensuring that the planets do not wander off into the lightless void. Astronomers often feel like cartographers trying to map an ocean while standing on a single grain of sand. We look out from our small vantage point and try to measure the height of mountains we can never climb. Beyond our atmosphere, the very concept of up and down dissolves, replaced by a sense of inward toward gravity and outward toward the unknown. As we drift away from the sun, the light begins to thin. The warmth of the hearth fades, replaced by the bracing, silent cold of the interstellar medium. This is the space between the stars, a realm that was once thought to be empty but is actually filled with the ghosts of dead suns and the seeds of new ones. Imagine walking across a frozen lake at night. The ice is thick and the air is still. In the distance, you see the faint glow of a cabin's window. That cabin is the nearest star system, Alpha Centauri. To reach it from our sun, even at the speed of light, would take over 4 years. If you were walking at a human pace, the journey would take tens of thousands of generations. You would be born, live, and pass away in the dark, as would your children and their children, all while the destination remained a distant, unwavering point of light. This is the neighborhood of our galaxy. It is a place of immense, lonely roominess, where the objects are islands separated by oceans of silence. What makes this strange is not just the distance, but the time. Because light takes time to travel, looking into the distance is a form of archaeology. When you look at a star that is 20 light years away, you are seeing it as it was 2 decades ago. You are seeing a ghost of the past, a lingering image that has been traveling through the vacuum just to reach your eyes. This challenges how we think about now. In the universe, there is no universal now. There is only the perspective of the observer, caught in a slow-motion replay of cosmic history. As we move further out, we encounter the true giants, the stars that defy the limits of stellar physics. There are stars like Betelgeuse, a red supergiant that is so large it would swallow the orbits of Mercury, Venus, Earth, and Mars if placed at the center of our system. It is a bloated, dying sun, a majestic structure of gas that is preparing to return its material to the galaxy. These giants exist in a state of quiet equilibrium, balancing the inward crush of gravity against the outward pressure of their own light. They are the elders of the stellar community, reminding us that even the most massive objects have a life cycle, a beginning, and an inevitable conclusion. But even these stars are not the largest objects we have found. They are merely the building blocks. To find the true titans, we must look at how these stars gather together. They form clusters, and those clusters form galaxies, and those galaxies form the great filaments that weave the cosmic web. This hierarchy of scale is a fundamental rule of the universe. Small things make large things, which in turn make impossibly large things. It is a nested reality, like a series of boxes that never ends. There is a mild awe in realizing that the atoms in your own body were once forged inside the hearts of these giants. The carbon in your cells, the iron in your blood, and the oxygen you breathe, were all created in the nuclear furnaces of stars that lived and died long before the Earth was even a cloud of dust. You are a part of this scale expansion. You are the universe's way of looking back at itself and saying, I am very large, and I am very old. As you lie there, let the weight of this perspective ground you. You are safely tucked away in a quiet arm of the Milky Way, far from the chaotic centers of galactic collision. You are shielded by the sun's magnetic breath and anchored by the Earth's steady gravity. The vastness of the cosmos is not a threat, it is a context. It is the backdrop against which your life unfolds, providing a sense of scale that makes your daily worries feel as light as a photon. We are preparing to move beyond the individual stars. We are going to look at the structures that hold billions of suns in their grip. We are moving toward the great attractors and the walls of galaxies that span the observable horizon. But for now, just breathe with the Sunday. Feel the slow, heavy pull of the solar system as it moves through the galaxy. There is no rush to understand the whole picture at once. The universe has been here for 13 billion years, and it is perfectly happy to wait for you to catch your breath. The definition of an object has already begun to shift in your mind. It is no longer just a stone or a tree. It is a system. It is a relationship. The largest object we've ever found is not a solid thing you could kick with your foot. It is a pattern of matter and energy so vast that it defines the very shape of space. To see it, we must continue our journey outward, past the familiar stars, into the deep, echoing halls of the superclusters. But for tonight, this human-scale perspective is enough. It is a bridge between the world you know and the universe you are part of. It is a calm, stable platform from which we can observe the infinite. Let the light of the sun, now a distant and gentle memory in the dark, be your guide as we step into the next loop of our expansion. And for now, that uncertainty, the sheer impossibility of the scale, is simply part of the picture. It doesn't need to be resolved. It just needs to be felt. With that in mind, let's move outward once more, to a scale where stars are like grains of dust and galaxies are the only objects that matter. Dark expanse, untouched and silent, a world frozen before human ancestors ever discovered fire. Its journey inward becomes a pilgrimage, a rare awakening from an existence mostly defined by stillness. You allow that thought to settle in your mind like a snowfall, slow, quiet, inevitable. Turning your attention to the interior, you picture layers of organic molecules preserved within the ice. These molecules carry the signatures of chemistry that predates life on Earth. Some may be precursors to the building blocks of life itself. You reflect on the scientific theory that comets like this one might have delivered essential ingredients to early Earth, seeding the young oceans with materials that helped life begin. The comet becomes not just a witness to the past, but a participant in it, a traveler that may have played a role in the emergence of life. This possibility expands your sense of connection to the comet, as though its long journey is intertwined with your own story. You imagine a fragment of the comet breaking off, drifting through space, eventually falling toward Earth in some distant age. This fragment enters the atmosphere, heating briefly before landing softly on an ancient plain. Inside that fragment lies a molecule that will someday become part of something living. You feel a gentle wonder at this possibility, knowing that life is a series of connections stretching across time. The comet becomes a reminder that you, too, are part of an ancient chain, shaped by events that occurred long before your birth. As the echoes continue to unfold within you, you realize that the comet is not simply telling a story. It is inviting you to remember something about yourself. It reminds you that time is vast, that change is slow, and that endurance often comes from stillness rather than motion. You let this reflection settle softly, feeling its quiet truth expand within your chest. The ancient world carried by the comet mirrors the ancient world carried within every person, the one made of memories, instincts, and stories passed down through generations. The comet rotates slowly beneath you, revealing a cluster of crystalline ridges glinting in sunlight. These ridges formed early in its history, shaped by interactions with cosmic radiation. You imagine them as frozen sculptures, untouched since the earliest days of the solar system. Their beauty lies not in perfection, but in endurance, the way they stand unchanged despite the passage of millions of years. This endurance becomes a metaphor for the human experience, the way certain memories remain bright even after time reshapes everything else. As the comet moves steadily toward the inner solar system, you feel the echoes begin to shift again, as though preparing to lead you toward a broader view. The past is rich, deep, and endlessly fascinating, but the universe is always nudging you to expand your perspective. You sense the transition forming, a gentle widening that pulls you outward. And yet, even now, the universe seems to whisper that to understand this ancient traveler fully, you must lift your gaze from the past and look toward the vast expanse waiting beyond the horizon, where the cosmic perspective unfolds in quiet, shimmering light. And yet, even as the echoes of ancient memory drift quietly across your awareness, like frost carried on a slow wind, you feel the universe beginning to expand around you again, opening not backward, but outward, widening into something larger than history. The comet continues its patient glide, but now its presence becomes a doorway, a quiet threshold, inviting you to step beyond the intimacy of its frozen past and into the boundless stage upon which it performs its long, deliberate journey. You sense the shift, the way one notices dawn easing across a horizon, subtle at first, then unmistakable, filling everything with new light. The past was deep, but the cosmos is deeper, and your thoughts gently tilt upward, drawn toward the enormity that always surrounds you, even when you forget to look. You imagine yourself drifting farther from the comet now, giving it space so you can see it in context. It hangs like a dark, textured ember against a canvas of stars that stretch in every direction, silent and indifferent, yet somehow comforting in their vastness. The beauty of this view is not in its detail, but in its scale. Everything becomes quieter as you float here, as though distance itself has softened the noise of human thought. The comet no longer appears as a solitary traveler. It becomes part of a great, swirling choreography of planets, light, dust, and invisible forces shaping the motion of entire worlds. You feel the cosmic perspective settling into your chest like a slow, deep breath. As you rotate gently in this stillness, your gaze catches the faint glow of distant galaxies, each one a sprawling archipelago of stars. You imagine what it would be like to drift among them, each cluster containing billions of suns, each sun potentially hosting its own worlds, each world perhaps sheltering life that dreams in its own way. The scale becomes so immense that your mind cannot hold it all, yet it tries, stretching like a quiet tide to accommodate the immensity. The comet becomes a tiny note in a universal symphony, and yet a meaningful one, because even the smallest notes change the shape of the music. You feel yourself softening into this realization, allowing the enormity to calm you rather than overwhelm you. Your thoughts turn to the gravitational forces that guide the comet's immense orbit. You picture the sun not as a blinding disk, but as a soft sphere of light, pulling gently on everything around it, shaping the trajectories of planets, asteroids, dust, and icy wanderers. The sun's gravity extends far beyond sight, reaching into regions so distant that its influence feels more like a memory than a force. And yet it persists, guiding the comet inward after millions of years in the frozen outskirts. You imagine gravity as a quiet hand resting on the comet's shoulder, not pushing or pulling abruptly, but reminding it which direction home lies. You consider how this same gravitational hand shapes your own existence without you ever feeling it directly. The Earth rests in its orbit because of this cosmic choreography, spinning through space with a grace so reliable that most days you forget to marvel at it. The comet becomes a reminder that motion is universal, that everything is in continuous, unbroken movement. You feel a soft humor in the fact that humanity, so proud of its schedules and routines, lives on a planet that spends every moment hurtling through space at unimaginable speed while pretending it is sitting still. Even the quietest night is not truly quiet. It is an endless voyage through a universe that never rests. The stars shimmer more brightly as you look across the sky, revealing constellations whose shapes have been recognized for thousands of years. You imagine ancient astronomers tracing these patterns, assigning stories and gods to the stars, trying to make sense of the enormous canvas overhead. Their interpretations may have differed, but their awe was the same feeling that rises inside you now as you let the cosmic perspective widen your vision. You imagine those early stargazers sitting beside fires, pointing upward, whispering questions in languages lost to time. You feel connected to them, a quiet link forged through wonder. Your gaze shifts to the galactic plane, that luminous band stretching across the darkness. It is composed of billions of stars, dust lanes, and clouds of gas glowing softly in scattered starlight. You imagine drifting closer, weaving through massive nebulae where new stars are born. These stellar nurseries stretch across light years, immense clouds of hydrogen shaped by pressure, temperature, and gravity. The cosmic perspective reminds you that creation is not a single event, but an ongoing process, unfolding in every direction. The comet you follow was formed from similar clouds, gently drawn together into a solid body by forces so patient that they operate across eons. You imagine drifting still farther outward until the solar system shrinks to a tiny point of light. From this vantage, everything familiar becomes small, almost fragile. And yet there is something reassuring in that smallness. It reminds you that the universe is immense enough to absorb every worry, every mistake, every uncertainty. Your perspective widens until even the comet's long journey feels like a brief flicker in a great ocean of time. You sense a gentle humility rising inside you, softened by the knowledge that you are part of something vast, ancient, and ongoing. As you float in this expansive stillness, you think about the human desire to understand the universe. Scientists spend entire lifetimes studying light, gravity, motion, particles, and energy, yet the cosmos remains full of mysteries. You picture a NASA astrophysicist standing in a quiet laboratory late at night, illuminated by the glow of computer screens. They examine new data from a distant observatory, watching the comet brighten as it approaches the sun. The scientist rubs their eyes, sips cold coffee, and smiles, knowing that this small piece of information contributes to a much larger understanding. Their dedication mirrors the comet's patience, both moving steadily toward deeper revelation. The cosmic perspective deepens as you reflect on the nature of time itself. The comet moves slowly, yet its orbit spans millions of years, connecting the past, present, and future in a single arc. Time stretches differently here, becoming less linear, more fluid. You imagine watching the comet's entire orbit from above, a long ellipse drawn like a thread across the solar system. The comet is currently at one tiny point on that thread, but its path stretches far beyond what any human lifespan can encompass. This thought reminds you that your own life is part of a larger continuum, a brief moment in a story that began long before you and will continue long after. You let this understanding sink in, feeling the softness of its truth. The cosmic perspective does not diminish your existence. It enlarges it by placing it within a vast context. Every breath you take becomes part of a cosmic rhythm. Every thought, a reflection of the universe's capacity for complexity. You are made of atoms, forged in ancient stars, shaped by forces that operate across billions of years. The comet becomes a companion in this realization, a reminder that even solitary wanderers are connected to everything around them through the invisible threads of physics and time. You imagine the comet continuing its slow rotation, revealing surfaces shaped by countless encounters with cosmic radiation. Its texture tells stories that span ages, illuminated now by sunlight that has traveled across millions of miles. This sunlight carries the imprint of nuclear reactions deep within the sun's core, reactions that will continue for billions of years to come. You imagine riding a beam of sunlight from the sun to the comet, feeling the gentle warmth slipping across the frozen surface, waking ancient molecules with a soft touch. This simple interaction becomes a metaphor for awareness, the way small insights can awaken memories or stir new understanding. As your thoughts settle into this expansive calm, you begin to sense the gradual return of introspection. The cosmic perspective is vast, but the human mind eventually begins to look inward again, drawing meaning from the grand view. You feel a gentle tug guiding you back toward yourself, back toward reflection, back toward the human experience. And yet, even now, the universe seems to whisper that to understand your own place within this vastness, you must descend from the cosmic view into the quieter terrain of human meaning waiting in the next unfolding moment. When we think about the largest galaxy in the universe, we often imagine it in human terms. We try to use distances we can walk or time we can measure in years. But human scales are like a small candle held up against a vast, dark ocean. To understand where we are going, consider a simple walk. If you were to walk at a steady pace, without stopping for sleep or food, it would take you about a year to walk the circumference of the Earth. That feels like a significant distance, a long, weary journey across continents and seas. Now, imagine that journey scaled up. If you were to drive a car at highway speeds toward the sun, it would take you about 193 years to arrive. Multiple generations of your family would be born and grow old within that car before the dashboard clock reached its destination. That is just our local neighborhood. When we talk about galaxies like IC 1101, our human measurements, miles, kilometers, even the distance to the sun become almost humorous in their inadequacy. They are like trying to measure the volume of the Pacific Ocean using a single teaspoon. This comparison isn't perfect, but it gives us a calm place to begin. It allows us to recognize that our smallness isn't a limitation, but a starting point for wonder. To understand the giant, we must first understand the grain of sand. We must look at the tools we carry in our pockets, the rulers, the clocks, and the maps, and realize that they were designed for a much smaller house. Consider the simple act of walking. For a human, a walk across a meadow is a pleasant way to spend an afternoon. A walk across a continent is a feat of legendary proportions, something that would take months of steady, rhythmic effort. If you were to set out on foot to circle the entire Earth, you would be walking for nearly a year without rest. Your shoes would wear thin, the seasons would change around you, and by the time you return to your starting point, the world would have aged. To us, the Earth is the definition of vast. It is the horizon that never ends, the solid ground that holds everything we have ever known. But if we step just 1 inch away from the Earth's surface, our perspective begins to stretch. Imagine a car traveling at a steady speed on a long, straight highway. If that highway led to the moon, you would be driving for about 6 months. It would be a quiet trip, a long period of looking out the window at the approaching white sphere. But if you turned that car toward the sun, the journey would change. To reach the sun at highway speeds, you would need to drive for 193 years. You would not finish the trip. Your children would not finish the trip. It would be your great-great-grandchildren who finally felt the warmth of our star growing closer. This is the scale of our local neighborhood, a distance that already exceeds the span of a single human life. Yet, even this 193-year journey is a microscopic flicker. To a galaxy like IC 1101, the distance between the Earth and the Sun is practically zero. It is a rounding error. It is the thickness of a single coat of paint on a skyscraper. When astronomers look out into the deep field, they have to stop using miles and kilometers entirely. These numbers become too heavy to carry. They have too many zeros. They clutter the mind and lose their meaning. Instead, they use light. Light is the fastest traveler in the universe, moving at 186,000 miles every single second. In the time it takes you to blink, light has already circled the Earth 7 times. It is a speed so fundamental that it defines the rhythm of existence. To light, the trip to the moon takes a little over 1 second. The trip to the sun takes 8 minutes. If the sun were to suddenly go dark, we would continue to live in its warmth and light for 8 minutes, unaware that the source had vanished. We are always living in the recent past. But even light, as fast as it is, begins to feel slow when we look toward the larger structures of the universe. To cross our own galaxy, the Milky Way, light must travel for 100,000 years. This means when we look at the stars on the far side of our home, we are seeing them as they were when early humans were first beginning to use stone tools. We are looking at a ghost of a time we cannot remember. Now, hold that 100,000-year journey in your mind. It is a vast stretch of time, spanning the entire history of our species. And then, consider IC 1101. This galaxy is so large that light requires 6 million years to cross it. 6 million years. When a photon of light begins its journey at one edge of IC 1101, our ancestors on Earth were not yet human. They were distant relatives, wandering the forests of Africa. By the time that photon reaches the other side of the galaxy, civilizations have risen, built pyramids, invented electricity, launched satellites, and perhaps faded away. The galaxy is so wide that it contains the entirety of human evolution within a single crossing of a light beam. This scale is not meant to be frightening. It is meant to be a release. When we realize that a single object can be so large that it dwarfs our entire history, our daily anxieties begin to lose their weight. The deadlines, the small worries, the brief tensions of a Tuesday afternoon, they do not exist on the scale of 6 million light-years. They are absorbed by the golden glow of 1,000,000,000,000 stars. In the Abell cluster, where IC 1101 resides, time moves with a different gravity. It is a slow, heavy time that does not care for the ticking of a wristwatch. Think of a single star in our sky. It is a massive, burning ball of plasma, millions of times larger than the Earth. Now imagine 100 billion of those stars. That is our Milky Way. Now, try to imagine 100 trillion stars. That is the population of IC 1101. If every star in that galaxy were a single grain of sand, you would have enough sand to fill a beach that stretches across the entire planet. Not just one coastline, but every continent, every desert, every mountain, covered in a thick layer of stars. And each of those stars is a sun, potentially holding planets, moons, and rings of ice. We often imagine galaxies as flat spirals, like the ones we see in textbooks, but IC 1101 is an elliptical galaxy. It is a great, swollen orb of ancient light. It doesn't have the youthful, frantic energy of a spiral galaxy with its new stars and bright blue gas. It is a collection of old souls, red and yellow stars that have been burning for 10 billion years. It is a retirement home for suns. It is calm. It is stable. It has reached a size where it no longer needs to rush. It simply sits at the center of its cluster, a gravitational anchor for thousands of other smaller galaxies that orbit it like moths around a campfire. To understand the mass of such a place, we have to think about gravity. Gravity is the quietest force, but it is the most persistent. It is the shepherd of the stars. In a galaxy as large as IC 1101, gravity is so strong that it bends the path of light itself. It pulls on the very fabric of space, creating a well so deep that anything nearby is eventually drawn in. Over billions of years, IC 1101 grew to its current size by eating other galaxies. It is a slow-motion consumer. It doesn't hunt, it simply waits. Smaller galaxies, distracted by their own internal dances, eventually drift too close. They are stretched, pulled apart, and woven into the golden fabric of the giant. This is not a violent act in the cosmic sense. It is a merger. It is a way for the universe to organize itself into larger and larger patterns. If you were standing on a planet in the middle of IC 1101, the night sky would not look like ours. Here on Earth, we see a few thousand stars and the dark, dusty band of the Milky Way. In the heart of the giant, the sky would be a solid, glowing canopy. There would be no true darkness. The density of stars is so high that the night would be as bright as a permanent twilight. You would be surrounded by the light of 1,000,000,000,000 suns, a warm amber glow that never fades. It would be a world without shadows, a place of infinite, soft illumination. But from our distance, IC 1101 is just a smudge of light in a telescope. It is a quiet reminder that the universe is capable of making things we cannot fully name. We call it a galaxy, but the word feels too small. It is a continent of light. It is a reservoir of history. It is a place where the laws of physics are the same as they are here, but the results are vastly more ambitious. As you lie here, safe and still, let the image of this golden giant rest in your mind. You are not required to measure it. You are not required to cross it. You are simply invited to acknowledge that it exists. Like a mountain in the distance, or the deep currents of the sea, it is there, whether we watch it or not. It moves with a slow, heavy grace, orbiting a center we can only guess at, participating in a cosmic cycle that spans billions of years. The teaspoon and the ocean, the grain of sand and the beach, the human and the galaxy, we are the small observers of the very large. And there is a profound peace in being small. It means we don't have to carry the weight of the universe. We don't have to manage the orbits of 1 trillion stars. We can simply drift. We can allow the scale of the giant to remind us that the universe is vast enough to hold all of our mysteries, all of our questions, and all of our silence. Scientists understand IC 1101 by watching the way the galaxies around it move. They see the dark matter that must be there to provide the extra gravity needed to hold such a massive structure together. They see the intracluster light, a faint, ghostly glow between the galaxies where stars have been stripped away from their homes and now wander the void alone. It is a complex, beautiful system, but at its heart, it is simple. It is a collection of light, held together by the same forces that keep your feet on the floor. Over the next few hours, we will move closer to this giant. We will look at its stars, its history, and its eventual fate. But for now, stay here in the human scale. Stay with the breath. Stay with the quiet. The giant is far away, and it is moving slowly. It is patient. It has been waiting for 6 billion years for its light to reach you. It can wait a little longer while you rest. Va. Everything is in its place. The earth is beneath you. The moon is above you. And the largest galaxy we've ever found is out there, glowing softly in the deep, a golden anchor in the dark. It is not a place of chaos, but a place of incredible ancient order. And as we begin our slow expansion outward, we do so with the knowledge that we are safe in our smallness, drifting in a universe that is far too big for anything but peace. To find comfort in this vastness, we must return to the simple things. We understand the weight of a hand, the length of a step, and the steady passage of the seasons. These are our anchors. Without them, the scale of IC 1101 would be too heavy to hold. But with them, it becomes a beautiful, distant horizon. Consider, for a moment, the concept of a neighborhood. In our daily lives, a neighborhood is a collection of streets, a few houses, and perhaps a park where the trees change color in the autumn. It is a place where you know the distance from your front door to the corner store. If you were to walk that distance, it might take you 5 minutes. In those 5 minutes, your heart beats a few hundred times, and the world remains exactly as you expect it to be. This is the scale at which we are designed to function. Our eyes are tuned to see the texture of a leaf or the expression on a friend's face. We are creatures of the local and the immediate. Now, imagine if we were to expand that neighborhood. If we look up at the moon, we are looking at an object that is roughly 238,000 miles away. To a human, that number is abstract. It is just a 2 and a 3 and an 8. But if you were to attempt to walk to the moon, it would take you nearly 9 years of continuous, non-stop effort. You would walk through every season 9 times. You would watch the constellations shift slightly in the sky. By the time you arrived, the world you left behind would have moved on. And yet, on the cosmic map, the moon is so close, it is practically touching us. It is the very first step on a staircase that has billions of flights. When we talk about the distance to the sun, the scale shifts again. It is 93 million miles away. If you were to fly in a commercial jet toward the sun, you would be traveling for 19 years. 2. Think of all that can happen in 19 years, the way children grow, the way cities change, the way we evolve as people. All of that time spent in a single straight line just to reach our own local star. This is the human scale, trying to grasp the solar scale. It is a stretch, but we can still just barely imagine it. We can look at the sun and feel its warmth on our skin, a physical connection to a journey that would take 2 decades to complete. The golden anchor of IC 1101 is always there, even when the sun is out and the sky is blue. It is there, glowing with the light of 100 trillion suns, silently holding its part of the cosmic web together. It does not demand our attention. It does not require us to understand its physics. It simply performs its role in the ancient order. It is a place of peace because it has already reached its final form. It is no longer struggling to grow. It is no longer burning with the hot blue fire of youth. It has settled into a state of graceful amber maturity. The universe is far too big for anything but peace. This is the ultimate lesson of the largest galaxy we've ever found. It is so big that conflict is impossible. It is so big that time is irrelevant. It is so big that silence is the only language that fits. And in that silence, we find our rest. We find our place. The golden anchor is waiting. The deep is calling. And we are safe in our smallness, drifting slowly into the heart of the ancient order. We find ourselves looking at a world that challenges every notion of habitability we once held. Nature often presents us with environments that seem far too hostile for any known biological life. The silence of the void is punctuated only by the steady pulse of a dying stellar wind. Some researchers suggest that the surface temperatures fluctuate wildly between the day and night side regions. If you enjoy these deep explorations in space, consider subscribing or hitting the like button. It really helps the channel grow and allows me to make content like this. We continue our journey through the data to understand the true nature of this strange place. The universe remains indifferent to our desire for finding a twin of our own blue home. Every measurement brings us closer to the quiet reality of our place within the vast cosmos. We move forward now into the deeper details of the light we have recently captured. The light from Proxima Centauri takes roughly 4 years to reach your eyes. It is a journey through a quiet, cold vacuum, crossing trillions of kilometers before it touches the sensors of our most advanced instruments. You are looking at a neighbor, yet it is a neighbor shrouded in a permanent, dim twilight. The star itself, a red dwarf, is smaller and cooler than our sun, glowing with a deep ruby hue that colors everything in its reach. As we settle into this observation, notice the stillness of the data. The James Webb Space Telescope does not see colors the way you do. it sees heat. It feels the faint warmth of a planet that never turns its back to its sun. One side of Proxima b is forever bathed in that dim red glow, while the other is trapped in a perpetual, frozen night. There is no wind to carry the warmth, only the steady, silent radiation of a star that has lived for billions of years. We are watching a world in equilibrium, a balance of fire and ice that has existed long before we looked up. The sensors are calm, the transmission is steady. We are simply witnesses to a distant reality. This planet, Proxima Centauri b, resides in what we often call the habitable zone, a term that suggests comfort, but here implies a different kind of intensity. To be in the habitable zone of a red dwarf is to be very close, tucked in toward the warmth like a traveler huddled over a dying ember. The orbit is short. A year on this world lasts only 11 Earth days. Imagine the speed at which it must travel to maintain its position, a silent, rapid circling in the dark, held tight by the gravity of a star that is much older and much slower burning than our own. We watch this motion through the fluctuations in the infrared spectrum, seeing the slight dip in light as the planet passes across the face of its sun. There is a profound patience required in this science, a willingness to sit in the dark and wait for the photons to arrive, one by one, carrying the signature of a world we may never touch. The James Webb Telescope provides us with a new way of feeling this distance. Instead of blurry pixels, we now have data points that describe the energy balance of the surface. We look at the thermal phase curve, a long and gentle wave that tells us how the planet heats up and cools down as it moves. The curve is sharp. It tells us that the heat does not travel well. On Earth, our thick atmosphere acts like a conveyor belt, moving the warmth of the tropics toward the poles and evening out the sharp edges of the day. But on Proxima b, the heat seems to stay exactly where it is dropped. The day side is a fixed bullseye of thermal radiation, while the night side remains a deep, unyielding well of shadow. This tells us something fundamental about the air, or the lack thereof. It suggests a world stripped bare, a skeleton of a planet that has endured the temperamental nature of its star for eons. As we continue to watch, we must consider the nature of the star itself. Proxima Centauri is an M-dwarf, a class of star that is notoriously active in its youth. While our Sun is a steady, yellow hearth, Proxima is more like a flickering candle in a drafty room. It produces flares that are hundreds of times more powerful than anything we experience. These flares are not just light, they are torrents of X-rays and ultraviolet radiation that slam into the planet's upper layers. Over millions of years, this constant bombardment acts like a cosmic sandblaster, slowly peeling away the layers of gas that might have once protected the surface. We see the aftermath of this process in the lack of water vapor signatures. We see a world that has been refined by fire, a place where the chemistry of life as we know it would find no purchase in the parched and irradiated soil. Yet, there is a strange beauty in this desolation. When we talk about a world that terrifies, we are often just describing a place that is indifferent to our presence. The landscape of Proxima b is likely a masterwork of geology, shaped by forces we can only simulate in our labs. Without the softening effects of rain or wind, the mountains would be jagged and sharp, their peaks reaching up toward a sun that never moves. The craters from ancient impacts would remain crisp and untouched, a chronological map of the solar system's history written in stone. There is a dignity in this permanence, It is a world that does not change because it has already reached its final form. It is a monument to the endurance of matter in a high-energy environment. We find ourselves drifting deeper into the data, moving from the broad thermal maps to the finer details of the minerals. The telescope looks for the silica feature, a subtle bump in the light that would indicate the presence of rocks similar to those in our own deserts. We find traces of basalt and iron, the heavy elements that settled into the core of the planet when it was still molten and young. The chemistry is familiar, but the context is alien. On Earth, iron is the heart of our magnetic field, a spinning dynamo that protects us from the sun. On Proxima b, we do not know if such a shield exists. If the planet is tidally locked, its rotation might be too slow to generate a protective bubble. It sits exposed, a naked rock in a sea of radiation, enduring the star's gaze without blinking. This leads us to a moment of quiet reflection on the nature of habitability itself. We often search for Earth-like worlds, but perhaps we should be searching for the limits of what a world can be. Proxima b is a baseline, a testament to the extremes of the cosmos. It tells us that a planet can be the right size and the right distance and still be a place of absolute, crystalline silence. The terror we feel is the terror of the void, the realization that life is a delicate and rare occurrence in a universe that is mostly made of radiation and vacuum. We are looking at our nearest neighbor and finding a mirror that reflects back the sheer luck of our own existence. The contrast between our green world and this red shadow is a lesson in cosmic humility. The data transmission remains steady. The telescope is a silent sentinel, orbiting a point in space, far from the interference of Earth's warmth. It is cold out there, almost as cold as the night side of the planet it observes. This shared coldness creates a resonance between the observer and the observed. We are using a frozen machine to study a frozen world. The precision is staggering. We are measuring temperature changes of just a few degrees from trillions of kilometers away. Each pixel of data is a precious commodity, a tiny spark of information that has traveled through the dark to tell us that we are not alone in the universe, even if our neighbors are made of silent stone and irradiated dust. As we transition into the next phase of our observation, we look toward the horizon of Proxima b. If you were to stand at the edge of the day side, in the permanent sunset of the Terminator line, the sky would be a deep, bruised purple. The stars would be visible even during the day because there is no thick air to scatter the sunlight into a bright blue canopy. You would see the constellations of our own sky, but they would be shifted, rearranged by the perspective of a 4-light-year journey. Our own sun would be a bright, steady star in the constellation of Cassiopeia, a small yellow dot marking the place where you were born. From there, Earth is just a memory, a tiny flicker of light lost in the glare of a much larger universe. The silence of Proxima b is not an empty silence. It is a heavy silence, filled with the history of a world that has survived the birth and middle age of its star. It is a silence that invites us to slow down, to match the pace of the cosmic clock. There is no need for fast conclusions or sensational headlines. The reality of the planet is enough. It is a world of extreme contrasts, a place of fire and ice, a neighbor that remains forever out of reach. We watch the data stream in, the long, slow lines of the infrared spectrum, and we feel the weight of the distance. The universe is vast. and we are just beginning to learn the language of the stars. The sensors are calm, the transmission is steady. We are simply witnesses to a distant reality. We watch the red dwarf glow, a steady ruby in the dark, and we wait for the next photon to arrive. There is a deep peace in this waiting, a sense of participating in a process that is much larger than ourselves. We are the eyes of the galaxy, looking back at itself, trying to understand the many ways that a planet can exist. Proxima b is one of those ways, a harsh, beautiful, and silent way. It remains there, locked in its orbit, a quiet companion in the dark until the end of time. The scale of this observation forces us to rethink our place in time. A single orbit of Proxima b is a mere heartbeat in the life of the universe. 10 days pass, and the planet has completed a journey that takes our own world a full year. This rapid cycling creates a sense of urgency in the data, a flicker of movement in the otherwise static void. Yet, despite this speed, the planet's face never changes. The same craters are always illuminated. The same plains are always in shadow. It is a paradox of motion and stillness. We are observing a world that is rushing through space at incredible speeds, yet it is trapped in a frozen state of existence, a prisoner of its own sun's gravity. As the James Webb Telescope continues its mission, it will look at other planets, other stars, and other galaxies. But Proxima b will always be special because of its proximity. It is the first step in our journey outward, the first test of our ability to understand the worlds that lie beyond our own solar system. What it found was not a second Earth, but something perhaps more important, a reminder of the diversity of the cosmos. It found a world that challenges our definitions and expands our understanding of what is possible. It found a place of terrifying beauty and profound isolation. And as we continue to watch, we find that the more we learn about Proxima b, the more we learn about the precious, fragile nature of the blue world we call home. The data remains steady. The light continues to fall on the gold mirrors. We are here, and we are watching. To understand the distance to Proxima Centauri b, imagine you are taking a very long walk. If you could walk through the vacuum of space at a steady, rhythmic pace, it would take you over 900 million years to arrive. Every step you take represents a tiny fraction of the void. If Earth were the size of a small glass marble on your table, Proxima Centauri would be another marble placed thousands of kilometers away. The planet itself is slightly larger than our own, a heavy rock hanging in the dark. If you stood on its surface, you would feel a bit heavier, your footsteps more deliberate and grounded. The sun in the sky would look much larger than ours, a bloated, dark orange disk that never sets. It would sit motionless on the horizon, casting shadows that never move, never shorten, and never lengthen. Time, there does not feel like time here. There are no Tuesdays. There are no mornings. There is only the long, unchanging now. It is a world where a shadow cast by a rock today will be in the exact same place 1,000 years from tonight. It is a slow, heavy existence, far removed from the frantic spinning of our own world. On Earth, we are defined by the cycle of the sun. We wake with the light and sleep with the dark. Our bodies are tuned to a 24-hour rhythm that governs our hormones, our moods, and our very sense of progress. But on Proxima Centauri b, that rhythm is broken. Because the planet is tidally locked, there is no rotation relative to its star. If you were to stand on the day side, the sun would hang in the sky like a heavy, unblinking eye. It does not move from east to west. It does not set. It simply exists, casting a long, still shadow that becomes a permanent part of the geography. The light from distant galaxies continues its journey across the expanding spaces of the universe, moving through the quiet void toward our waiting telescopes. The instruments we place in orbit around our planet maintain their silent watch, gathering the faint signals that drift in from the edges of the observable cosmos. Each photon that strikes a digital sensor carries a fragment of information from a time before our world was formed. We track the slow rotation of distant spiral arms and the gentle collapse of interstellar gas clouds forming new generations of stars. The radio waves they broadcast grow weaker and more diffused as they spread through the immense volume of space, blending into the natural background radiation of the cosmos. On Earth, the giant dish antennas of the Deep Space Network remain pointed toward the predicted coordinates, listening for the faint signatures of our technological children. We watch these slow changes with a patience born of understanding the true scale of the environment we inhabit. The universe remains wide and open, a quiet expanse where time moves like a slow river through banks of dark matter and luminous stars. Our thoughts drift along with the automated probes, coasting through the long valleys of gravity that define the shape of space. We find our place within this grand system, not by attempting to dominate or accelerate its processes, but by aligning our understanding with its true scale, accepting the vast distances and deep timelines as essential features of a beautiful and complex cosmos. As the light from the furthest stars continues its long journey through the night, our thoughts remain anchored in this serene awareness, floating quietly along the invisible lines of gravity that guide our world through the infinite, peaceful dark.